Hello, I am Devin Rorabaugh, and I'm an engineering software developer at Applied Flow Technology. So this webinar, I'll talk about how to model compressor head versus flow curves and all of the ins and outs of it. So we got quite a bit I'm going to cover. To start, I'll do just a brief overview of our compressible flow products. And then as review to kind of build up to the compressor head curves, I'll talk about pump head curves and their nuances and static versus stagnation properties, some of the nuances of that. Then I'll get into what an actual compressor head curve looks like and how compressor head kind of comes from thermodynamics and it's very different than pump head curves. And we'll actually start talking about those polytropic head and isentropic head curves that I'm sure plenty of you have seen from manufacturers. We'll talk about the flexibility of those curves and why they're the preferred way of modeling your compressor. Then some of the limitations of those. Then finally, we'll show how you can model your head versus volumetric flow curve in AFT Arrow and kind of review the key takeaways. So let's get into it. So we have a few compressible flow products. I'm sure you're familiar with AFT Arrow if you want to model compressors, because that's our steady state gas flow product. Now, Arrow for a cost has an XTS module. And if you get that and enable it, you can do slow transients. So slowly adjusting valves and operating conditions based on control logic, charging and discharging of tanks, all going in a slow manner. Anything where the transient's slow enough that there's not really flow discontinuities or mass flow discontinuities in the system, or there's not these transient waves bouncing around that you need a model, XTS can handle that. Now, if you do need to model those rapid transients and the pressure spikes from slamming a valve, quick discharging, effects of line packing where you see that mass flow discontinuity, then you need extreme. On top of that, if you want to model a reciprocating compressor and see how that reciprocating compressor's steady pulsation affects your system, see how it interacts with the natural frequencies of your system, and if it's causing pressure versus frequency responses that exceed API 618's limits, then you would want to use Extreme's PFA module. So that's a quick overview of our products. Let's get into the review. So I'm sure if you're working with compressors, you're very familiar with pumps or with the incompressible head curves. As you probably know, for pumps, head rise versus volumetric flow curves are the most flexible to you. They represent the inherent properties of the pump and are independent of the flow properties as much as possible, which is what makes them nice, right? So they calculate that that head rise, which is can also be known as a rise in energy grade line, and that's the stagnation pressure rise across the compressor divided by your density and gravitational constant. And if it is a very vertical compressor, I meant pump. If it's a very vertical pump, then there would also be that delta Z for the elevation change. rearranging that for your head curve for your pump, you can get your stagnation pressure rise, which most of the time people say, hey, that's just my static pressure rise, because the static and stagnation may not be too different, but I'm just being specific there. And then from your volumetric flow, or your capital V dot here, you can calculate your mass flow just by multiplying it by the density. These allow reliable calculations of pressure rise versus mass flow rate, because they don't depend on the liquid or the flow conditions. If the head versus volumetric flow curve was made with water and you're pumping with a different liquid than water, you can still reliably use that head curve. Of course, even pump head curves have limitations, right, on how flexible they are. They have, for example, a viscosity limitation. And for this, if the working fluid's viscosity is significantly different from the reference fluid or the fluid used to create the pump curve, its viscosity, then the head versus volumetric flow curve requires correction. And this correction for head value and correction for volumetric flow value have to be calculated. This is due to the effect of the fluid viscosity on frictional losses within the pump. Of course, the pump produces a pressure rise, right? But that pressure rise gets detracted from by the frictional losses in the pump. And those frictional losses depend on the fluid's viscosity. So if the fluid's viscosity is not too different from water, usually you don't need to do a correction. But if the pump was created, or the pump curve was created using water, and then you're pumping oil, then you would very much want to use this correction. Luckily, HI has a standard for that correction factor calculation, and we apply that standards methodology in Fathom by this option in the optional tab to use viscosity corrections. And then we also report those correction values to you. Since this is just kind of a review, for more information on viscosity correction in Fathom, you could go to docs.aft.com, click on the Fathom 13 Help Site button, and search viscosity correction. And we have plenty of details on how to do that. So lastly, on the pump head curve review, there's also kind of a speed limitation with pump curves or pump head curves. If you do just get one curve, well, typically you would get your range of speed curves, but you can correct that one head curve for speed with the affinity laws. The thing that I'm sure you know with that is these affinity laws are just, they're estimating the effects of speed on your head curve. So here on the side, you see that you can get your head rise based on your change in speed, and you can get your new volumetric flow based on your speed ratio as well. The thing is, these are estimates, like I was saying. So the best thing you can do is interpolate between your head curves for speed. Easiest way to do that is to find the head on the two closest speed curves. So say I'm operating at the speed between 1200 RPM and 1050. Then I can find my flow rate on these two curves and find the corresponding head values. Then I can interpolate for my actual head value on at my actual speed by interpolating for head based on my actual speed between these two speed values. And that's it for pump curves. It's just kind of a reminder of how they work and that even pump head curves have limitations. So just a reminder of stagnation versus static properties, since they matter for the compressor calculations and compressor head curves due to the additional complexity of compressible flow. As many of you know, if not all, stagnation properties are the properties the gas would have if it was brought to rest isentropically or reversibly. Gas stagnation properties are a function of the isentropic expansion coefficient and Mach number. Or for the simplest one, stagnation specific enthalpy, or stagnation enthalpy with respect to mass is just the static stagnation enthalpy plus a function of velocity. So plus velocity squared divided by 2. What a few people don't know, and I didn't know for a while, is stagnation properties of a fluid can be calculated from 2 other stagnation properties. So just like how if you have 2 static properties like pressure and temperature, you can get enthalpy, or pressure and enthalpy, you can get temperature. You can do the same with stagnation properties. So a weird stagnation property you'll see in these head calculations for compressors is stagnation compressibility factor, or Z naught. And that's just the compressibility factor at the stagnation pressure and stagnation temperature instead of static pressure and static temperature. So with that, we'll get into what head is for a compressor. So these polytropic and isentropic head versus volumetric flow curves are kind of they're the most flexible curve for compressors, just like the head versus volumetric flow curve is the most flexible curve for pumps. The thing that can trip people up is they see head, because sometimes it might not say polytropic head or isentropic head. In that case, you should ask the manufacturer which one they mean, or see if there's something else on the data sheet or any other information that tells you which one it is. Anyways, people see that head and they think it's the same head as the pump head, but it's very different. For a compressor, the actual head rise is the stagnation enthalpy rise per unit mass for that compressor, which it equals the shaft work per unit mass if you assume the compressor is well insulated and that it has a negligible velocity, or sorry, negligible elevation change between its inlet and outlet, which it almost certainly has. I don't think I can envision a compressor where the elevation change would be negligible. So actual compressor head rise, it's this enthalpy term, or enthalpy rise term, where in contrast, the pump head rise is this stagnation pressure rise per weight term, right? It's at delta P divided by rho G. So just keep that in mind when you're looking at these curves. And we'll go more into what that means for polytropic and isentropic head in a moment here. So polytropic and isentropic head are ideal values. They're the head rise across the compressor if it was a polytropic process, or head rise across the compressor if it was an isentropic process. We'll see the equations for those soon. But before we dig into the actual equations, I just want to cover one thing that when I started digging into these curves, it threw me for a loop, and it probably confuses other people. And that is that the polytropic or isentropic head can be in units of feet, meters, BTU per pound mass, kilojoules per kilogram, or even joules per kilogram. And so if it's a stagnation enthalpy rise, it's easy to envision, okay, BTU per pound mass or kilojoules per kilogram. And in the equations, we'll see that's easy to plug in. However, if you get it in feet or meters, you need to know how to convert it into more usable units like that BTU per pound mass or kilojoules per kilogram. So I have these little formulas below here. So you can see that for English units, if you divide the stagnation enthalpy rise, or that polytropic or isentropic head, by the gravitational acceleration constant, and you work out the units, then you'll see that the BTU per pound mass to feet has this conversion here. Now for the metric units, you can see that the conversion's nice 1-to-1, you know, as one might expect from metric. But this just shows how to get to those length units and get from those back to energy units that you would expect for your isentropic and polytropic head. So before we get into the equations, I'm going to talk just a little bit more about the theory behind these and things like that. So polytropic and isentropic head versus volumetric flow curves provide that flexibility. Once again, just like the pump curves do, they represent the inherent properties of the compressor and try to be as independent as possible of the actual flow properties and gas properties. That way, in an ideal world, you could take a compressor that its curve was made using air and use it for a very different gas. However, that has limitations, and we'll talk about those soon enough. So again, these head curves allow the user to reliably calculate pressure rise and mass flow rate of their compressor for those different gases and inlet conditions. And one thing to know when you're using these curves is you may think that the volumetric flow at the inlet obviously is different than the outlet of the compressor. So what do you go with the volumetric flow? And as many of you know, but just to solidify things and reduce confusion, these volumetric flow values on the curves are referring to the inlet volumetric flow. So as long as you use the polytropic head versus inlet volumetric flow, you get these very flexible curves that work with different inlet conditions, different gases. So what is polytropic head versus the actual head in terms of actually like putting the equations together? Well, our polytropic head here is that stagnation enthalpy rise for a polytropic process. And all that is the actual stagnation enthalpy rise multiplied by the polytropic efficiency. Now, I'm pretty sure I mentioned this on the next slide, but that polytropic efficiency, when you see an efficiency curve with your polytropic head curve, it will be the polytropic efficiency. And when the manufacturer provides an isentropic head curve and an efficiency curve, then that will be the isentropic efficiency. So same thing for the isentropic head. It's just that stagnation enthalpy rise for an isentropic process. And it's the actual stagnation enthalpy rise multiplied by the isentropic efficiency. So let's finally dig into the equations here. So polytropic head and isentropic head can be calculated with these top two equations here. Here's all the terms. So N is the polytropic coefficient, which you can see here. Gamma is the isentropic expansion coefficient. For ideal gases, that's the ratio of specific heats. Just keep in mind, if you're dealing with a real gas, it's not that simple. The formula is a little bit more complex, or you can calculate it with a property tool with pressure and temperature, or a set of tables. Just keep in mind that for real gases, it's not as simple as specific heat ratio. Then we have that mentioned compressibility factor at stagnation conditions, which you can see here in the two equations. The specific gas constant, as I'm sure you know, that's just the universal gas constant divided by molecular weight of the gas. Then we have our, put these opposite. That's funny, I didn't realize I did that. We have our stagnation temperature, T naught, and our stagnation pressure, P naught. So now that we know all of those, we can just look at our equations here and figure out how we get our discharge conditions for our inlet conditions. You'll see that mentioned polytropic constant, gamma, and stagnation compressibility factor in these equations. And in reality, those all change along the compression process, right? As pressure changes, as pressure increases and temperature increases, you would see a different ratio of specific heats, for example. You'd see a different compressibility factor. And typically in situations like that, you would average the inlet and outlet values. However, to avoid iteration, these values tend to be estimated as their inlet values. Just know that there's limitations in that. But if you're backing out your discharge pressure because you're doing hand calculations and you want to see if what arrow is spitting out lines up for the output, then you can treat those as the inlet values to do a rough cut hand calc. I mentioned before that when the user provides that polytropic head curve, then the efficiency will be the polytropic efficiency. And when they provide that isentropic head curve, then the efficiency will be the isentropic efficiency. That's important for these equations. So anyways, especially when you assume that these values are the values at the inlet, then with your known inlet conditions, you can back calculate your stagnation discharge pressure or stagnation outlet pressure. So if I have my stagnation enthalpy, if I have my polytropic head equation, then with all of my inlet values or inlet conditions, I can back out my stagnation outlet pressure. That's a bit easier, you'll see, for the isentropic head, and that's because the isentropic head is using the specific heat ratio term, or sorry, the isentropic expansion coefficient term, which, as I mentioned, isn't quite specific heats for real gases. But anyways, it uses that isentropic expansion coefficient term, which is easier to have available than the polytropic. The only difference, the only additional step you have to do for the polytropic is get your polytropic constant or coefficient from your gamma and your polytropic efficiency, which is once again from that efficiency curve from the manufacturer. And you just have to apply this equation to get this ratio, and then you have to apply the inverse of this to get this ratio here. So that's the only difference. Once you do that, you have your stagnation pressure at the outlet of your compressor, which is probably your main goal. But if you're continuing on calculations or validating Arrow further or something like that, then you'll probably want your stagnation temperature as well. That way you can use those stagnation to static equations I mentioned earlier to find your actual discharge static pressure and discharge static temperature. So how do you get that that discharge or outlet stagnation temperature? Well, you just take your efficiency value from your efficiency curve for your volumetric flow that the manufacturer provides on the curve, and you just either apply the polytropic equation here and back out the stagnation outlet temperature, or if you have an isentropic head curve, you would know that that efficiency is isentropic efficiency, and use this equation with all of your known values to back out the stagnation temperature at the outlet of your compressor. And that's the basics. That's how you get your compressor's discharge conditions using your polytropic head or isentropic head curve. So once again, I'm just going to mention that this is as flexible as it gets for compressor curves, at least as far as I know. And that's why it's really important to know these and to get these from your compressor manufacturer, especially if you're dealing with high pressure stuff where the flow is going to be compressible, because that flow is going to change with your inlet conditions. So as I just mentioned, the polytropic and the isentropic head versus inlet volumetric flow curves are mostly gas and inlet condition independent. The limitations on that are coming up, but that's what's nice about them. So if your compressor needs to deal with different gases or gas mixtures where the composition can vary, then these are the ideal curves for that. And you'll see those differences in the gas properties be reflected in your equation through gamma, compressibility factor, and the specific gas constant, right? Because the molecular weight change in your gas is going to affect your specific gas constant. Your critical point of your gas is going to affect your compressibility factor, and your gas is just going to have very different gamma charts or isentropic expansion coefficient charts versus pressure and temperature, if it just between different gases. So this makes the head curves great for mixtures where composition can vary. A very real example is you have your natural gas going to a gas turbine power plant, and sometimes or I guess technically all the time, the composition of that natural gas varies a bit, right? And if it varies significantly, then that's going to affect the molecular weight significantly. It's going to affect these values significantly. And you want to be able to account for that in your calculations when you're calculating your compressor discharge conditions and trying to figure out how these gas changes affect your system. So the other thing is the thermodynamic effects of changing inlet conditions, so inlet pressure and temperature, are accounted for as well through these equations. Even the velocity changing at your compressor inlet, because these are all stagnation properties. So you have to go from your static inlet conditions to your stagnation inlet conditions through the previous mentioned equations. And then when you get your discharge conditions, they're in stagnation again, and you have to convert them back to static. And that's just so that all of this variability of the inlet pressure, temperature, and velocity are all accounted for. So we have these very reliable curves, but nothing in reality is easy. So we have to figure out the limitations of these curves, understand them, so that we can make sure we know what we're doing and we can apply the curves correctly, right? So head curves capture the thermodynamic effects of changing properties and inlet conditions, as I mentioned. However, there are also aerodynamic effects of how the gases hit the blades and vanes or impellers within it. And there's also frictional effects. And both of these can significantly alter the head curve when conditions are too different from their design conditions. So even though this head curve is meant to be this very constant, reliable thing that you don't have to correct, it still can be affected by aerodynamic and frictional effects as your actual working conditions differ too far from the design conditions that the compressor is meant for. Now, this is something that has a lot of complexity, and it's the best bet to just talk to your compressor manufacturer, make sure that your compressor is designed for multiple intended conditions of your or operating conditions of your piping system, and they'll pick the best fit for you and pick curves that help you do calculations that relate to the actual inlet conditions and actual conditions you're seeing. But yeah, just keep in mind that that variation still exists. So if your gas has significantly different molecular weight or inlet conditions from the reference fluid, which is the gas that was used to create the curves, it's best to update the head curves with the help of the compressor manufacturer. And usually they can do this pretty quick and help you out. How you can tell that is manufacturers will provide this information of the reference gas, which is typically air, I would say, and the inlet conditions that they use to create the compressor curve. And if you're starting to think, okay, this is pretty far from the pressure and temperature I'm operating at, or my fluid is a very heavy fluid when it comes to molecular weight, and what they use is very light, or vice versa, then that's when you can reach out to them and get better compressor curves. So here's some examples of those effects that can alter your head curve and why they exist. So large differences in molecular weight, as I mentioned, will cause head curves to change. They specifically change by steepening with heavier gases and kind of like flattening out with lighter gases. Also, heavier gases will reach that stall line and start to stall out at lower volumetric flow rates than the lighter gases that you can see have more of an operation range before hitting any stall conditions. Large enough changes in Reynolds number can cause significantly different frictional losses through the compressor's geometry as well. So, its impeller, its casing, all that the fluid's flowing through, that still has frictional loss. And of course, as I mentioned with the pump, the compressor is still producing a pressure rise but it's just going to have more losses, more frictional losses to fight against as that Reynolds number, it increases, or especially if you go down and you get into the laminar region. I'm sorry, I may have said that wrong, but the frictional effects can be significant with a significant change in Reynolds number, especially if you went from the turbulent region to the laminar region. And that's something to keep in mind. So lastly here, as the gas compresses to different volumes than designed for, the velocities leaving and entering intermediate stages of the compressor can differ significantly from the design. And that's shown in velocity triangles. So as I'm sure a lot of you know, again, your rotor is rotating in a certain direction. So let's say here it's going down and your fluid's flowing in at a certain velocity. That's going to affect the vector addition of figuring out the velocity of your gas relative to your rotor blade. And the rotational speed, given you keep that the same, that's going to stay the same, and the velocity will change. Well, that's going to give you a different angle of your relative vector, and that's going to cause a different incidence on the rotor blade. Now, if that incidence angle is quite off, that can lead to greater flow separation and greater losses through the compressor. And that effect wouldn't really be seen so much on the inlet stage of the compressor, but if you have this very different gas, even though the head curve through the first stage, or the first rotor and stator, or the first impeller is going to be pretty much the same, you're going to get a different outlet pressure and a different outlet volume. And more specifically, because the volume is different, you're going to get a different velocity coming out of that first stage and into the next stage. Now that can cause a very bad incidence angle for your secondary stage. And now if you have multiple stages, that can compound over the multiple stages of rotors and blades or impellers. And that's just something to keep in mind. So these head curves are great and they're very flexible, but for multi-stage compressors, they can break down even faster than they would for a single stage. So, I mentioned kind of loose speed limitation and how speed affects your pump. I'm mentioning it here for the compressor head curves as well. So just like with the pump, pretty straightforward. The head curve is for a constant compressor speed. And you'll see that people will correct these compressor head curves for different speeds with the affinity laws. That is something you should do very carefully and maybe and avoid if you can. That's because this estimation of the affinity laws breaks down very quickly for compressible flow. It's assuming the flow is incompressible. And just like we were mentioning with the head curves, but to a much greater extent, multi-stage compressors will really break down the affinity laws. And I've seen a multi-stage compressor where within like 5% speed change, the error was 25%. So just keep in mind when you compared the adjusted affinity law or the head curve that was adjusted by affinity laws to the actual RPM value of a different speed curve for that same compressor. So just be very careful using those. It's much better to do what I'm about to say here and interpolate between your head versus speed curves. So just like with the pump curves, you should do that. You should interpolate between your head curves. If they're nice and pretty flat like this, you can get away with using the flow on your two curves to get your head, then interpolating based on speed. However, for axial compressors, you should keep in mind that other interpolation methods may be required because you can get these very vertical curves where interpolating based on flow may not even be an option for you. So to kind of wrap things up here and actually get to the meat of it, we'll talk about using a head versus volumetric flow curve in AFT Arrow. Sadly, AFT Arrow cannot currently model isentropic head curves. However, if your manufacturer knows how to produce isentropic head curves, they should easily be able to produce polytropic head curves for you as well. As you saw, they're not that different. In a worst case scenario, you have the equations. It's easy to convert your isentropic head curves to polytropic head curves. And you can convert your isentropic efficiency to polytropic efficiency. So with that said, Arrow lets you enter the polytropic head versus volumetric flow curves. Remember, that's the inlet volumetric flow. And here's the steps to do it. So you would double click on your compressor in Arrow to open up your property window. And you just need to set the compressor model to curve. Compressor map's very specific to corrected mass flow or non-dimensional mass flow, so that's something different. But yeah, you just set it to curve, you set added pressure to stagnation, and then compressor and process thermodynamics need to be set to determine from efficiency data. That's just so you can get that polytropic constant from your gamma and your efficiency data, or so that we can get that for you. So once you select those three, you just hit or click the enter curve data button, and it takes you to your curve fit form. The important things to do here are in your flow drop down, make sure you're selecting volumetric for your inlet volumetric flow, and you select your flow units. You'll often see ACFM, which I'm sure you know is the actual cubic feet per minute. We like to represent that as this feet cube per minute term. So just if you're having trouble finding it, that's why. And our polytropic head, we have it in feet or meter units, as well as other length units. So that's our options. You would have to convert from energy units to put it in if your curve is in energy units currently. The efficiency data, we need that once again to figure out that polytropic constant, and also to figure out what the discharge temperature is based on the efficiency and the pressure rise across the compressor, or pressure ratio across the compressor that we figure out. So once you get that data in, I recommend doing an interpolated curve fit and having a lot of data points, definitely much more than 3. That's because your compressor curve, if you do a polynomial curve fit for these, can get this like upside down U shape or hill shape across different flow rates, and that can cause trouble converging in Arrow. So doing the interpolated data can help avoid that. Oh, and also we have a multiple configuration feature. You can find that on docs.aft.com as well, and that can help you enter multiple speed curves for your head versus inlet volumetric flow. So that's all the details. I just want to end with a quick note of the takeaways before I kind of do the final wrapping up. Those takeaways are: compressor head rise is very different from pump head rise. You know, compressor head rise is that enthalpy per mass term, where pump head rise is that pressure per weight term. And we saw how to calculate outlet pressure and temperature from our head curves. Straightforward enough for compressible flow, I think. We saw why head versus volumetric flow curves are very flexible, and therefore they're the preferred curves for really modeling the physics of your system and making sure you're not misrepresenting your compressor by thinking it's going to operate at a certain pressure and mass flow, right? If you have very different inlet conditions, your head curve will correct for those until it's, you know, too far gone. The fourth one here is that too far gone point. Even though head versus inlet volumetric flow curves are the most flexible, they still have limitations as well, and you need to be wary of those and know that they exist. Lastly, I showed you how to model that head versus volumetric flow curve in AFT Arrow. And with that, you'll be able to put your curves in Arrow and understand what's going on and better interpret your results. So, as always, we have great resources for you. We have many other webinars, tip and trick blogs, case studies, so you can see how other people in your industry have used our software, technical papers. Then we have consulting with our Flow Expert package. That's just having a dedicated engineer with a set number of paid for hours. That's if your questions are more engineering based, like, can I trust these results with these assumptions, things like that. Otherwise, if it's just simple questions and your company has a subscription with us, then by simple questions, I mean, you know, what does this feature do? How do I enter inputs for this? Or what is a head curve? Things like that. Then you can just call us and ask us, and we can help. We also have Purple Mountain Technology Group. This is for consulting, for a full-blown project. And I'm not the best person to talk to about that. You would just have to reach out to us and we'll get you set up with Ben, and he'll help you get started with that, but we offer that as well. So we have our help site, that docs.aft.com. Here we have all our documentation on how all our stuff works. We have example models. You'll see the equations and theory and more similar information. I think we have an awesome resource in that. And if you want to reach out to our support, once again, if it's not really the consulting kind of questions where there's ramifications for us helping you without a contract, then you can call our support team or reach out by this email here, and we'd be happy to help you out. That's definitely the greatest asset of our company. We really work to get back to you day of, and if not, then we typically get back to you by the next business day. And we'll keep you updated otherwise. And for any other questions on specifically this webinar, reach out to info@aft.com and we can get you more answers. All right, well, thank you, everyone. That's the webinar, and I hope you have a great rest of your day. And I hope to teach you more in another webinar in the future.